So we've spent some time understanding how these different logic blocks are put together and how we can combine them to form different HVAC sequences of operation. So we did things like this. Started with some simple blocks, put them together, created outputs and enables, used some different annotations to understand what these logic block diagrams look like on our design sheets and what they might look like inside our programmable controllers. So the goal is to be comfortable with these CLDs or logic block diagrams, being able to read them on as-builts, to create HVAC in this format, and to be able to think in this way that's so that when we actually interface with our programmable controllers to make some change, that we know how this type of format is, so that we can more or less speak this language of logic blocks. So this is what a typical control logic diagram design sheet might look like. We kind of broke down some of that structure, and then we looked at specific HVAC sequences of operations associated with different systems. We started with some simple things, we ended with economizers. Now we're going to circle back and look at some systems that are either a little more complicated or have some set point reset capability or typical application. So let's go back to the coils that we started with in the last video. So here's a heating coil we can see on the schematic. We see a number of different hardware inputs going to different places. For supply air temperature, we see how that's being fed back into this DDC controller and then presumably used in some PID loop to drive a heating coil valve command. So if we pull in different data like this outside air temperature, we can do different things like establish a reset or use that outside air temperature as a lockout set point. So for the reset, the logic behind it is this. For a coil, we may understand that at design conditions, say as cold as we really expect it to get, about 0 degrees, that a designer may have established 100 degrees as the heating coil discharge set point that you need for that worst case scenario. Understanding that we're not always at that worst case scenario, and that as the temperature increases outside, so with outside air temperature being the driver of the reset, we would start resetting that set point down all the way down towards 80. So this is what that linear reset looks like. We're linearly resetting the set point down from 100 degrees to 80 degrees of coil discharge as it gets warmer outside. So another thing that we can do is kind of map these points. So at the design condition, we have these X1, Y1 pairings. And at the low end of the reset, we have this X2, Y2 pairings. And that's important not only to be able to map that we have indirect control action, but when we actually use the logic blocks for reset, this may be how it's designated on a design sheet, that you have outside air temperature driving this reset for set point. But really what's behind that and what may be annotated in the control blocks inside the controller is that you have this pairing, and to establish the reset range in a control system, you'd have to match up the design conditions in that X1, Y1 with those secondary or low end of the reset conditions here as the X2, Y2. So some thoughts before we move on. We used outside air temperature here as the driver of the reset, but that's not always the only reset available or even the best reset. When you get into resetting things associated with cooling, outdoor air reset may be one energy driver, but you may have things, especially for interior zones, like ventilation loads or how many people or what equipment is in a space, that's going to be a better driver for what your load is. How can you put in some safety into this logic? So if we've put a reset in and it's not working, i.e. the zones are not happy, how can we feed that back into our reset or have some ability to automatically ignore or back off of the reset? So there's different ways to do that. And what happens when we have multiple resets acting in competition with one another? So here we have a air coil discharge set point reset. What if we had a hot water supply temperature reset as well? Can we do those together? Should we do one, and then if we still are in low load, do another? So there's different ways to do that, and if you have multiple control loops, you want to have good coordination from one to the next. So let's revisit our economizer and consider now how we might control minimum outside air going through the outside air end of the economizer. So what's shown here is a minimum air damper, sometimes called or could be run as a two-position damper. And there's different ways that we might be able to control this. So there's 4 basic ways that I can think of. You could have a two-position damper where you have this binary open and closed damper that runs with the system. You could have a modulating damper, so where you have a single economizer damper for outside air. You may have some chock block or some minimum damper position that you may run that at that is ideally balanced by somebody like a tab person to establish what that minimum position is at the damper and how that correlates to the minimum airflow that you want. You could have a modulating damper that uses flow station data, so with some extra hardware input, i.e. a flow station, you could have that driving a control loop that is controlling your CFM set point through that outside air inlet. And you could have something like demand control ventilation, where we're resetting the minimum outside air set point, and we could be using something like CO2 in a zone as a proxy for how much minimum air we need at a given moment. So here's what that two-position control block logic would look like. It's pretty basic. We have a system enable, so either when the fan's on or when the schedule says that we should be in occupied mode, we have a basic switch block. So we can either be fully open or fully closed, and that would be the binary or digital output going from the controller to this minimum outside air damper actuator. We could also have a control loop where we have something like a flow station as a hardware input, as shown here with this analog block, being compared to the minimum outside air flow set point, ran through your PID block depending on your P and your I factors or settings. That's going to change your minimum outside air damper command. So this would be, for a demand control ventilation setting, what we would actually reset. As an alternative to resetting, what you might have is zone CO2 driving the control loop itself and changing the position of a minimum outside air damper. But some general thoughts about how we may do these things. So when we use CO2 as a proxy for occupied load, we have to understand that there's some synonymous nature with CO2 and poor calibration or error. So they can be maintenance prone devices. There's a certain reliability issue right now that folks report from the field, and where you have a lot of zones, it may not be a good application to put CO2 sensors in each zone and then try to have that drive your minimum outside air position. We might want to look at the climate we're in and consider, does it really make sense to worry a whole lot about resetting minimum outside air? Well, if you're in a climate that's going to be economizing all the time anyways, where you're at 100% air for very, very large chunks of the year, then having this ability to reset, which is really a way to take away ventilation load, either on the heating or the cooling side, that may not make as much sense or may not pay back as much to add that complexity. And when would two-position control be better? So if you have large dampers, a lot of CFM going through a system, and you have relatively low minimum outside air loads, it may be tough for a single damper assembly to try to control to that low CFM, making a two-position application a little bit more convenient. So what do we have here? Well, we talked about the supply fan control loop in the last video. So here we see something like duct static pressure being read out in the distribution, being sent back to a DDC controller that then is sending out a supply fan start-stop and a supply fan command or speed to the VFD. So this is what we would call our supply duct static pressure control loop. So we're controlling to some duct static pressure out in the zones and changing the speed to maintain that. So another pretty basic control loop when we have a PID block comparing the actual supply air pressure to what our set point should be. But this is another opportunity we have to reset that supply air pressure set point. So a few things to keep in mind when we're doing that. So essentially what we're trying to do is take some design number, which is typically around 1.5 inches for water column at that duct static pressure sensor, and lower it to something closer to maybe 1/2 inch, maybe 3/4 of an inch, maybe an inch. Whatever you still may need in those low load conditions to bring the CFM to your boxes and still have enough static pressure to get it past the boxes and into the zones and through the diffusers in the correct way. But recognizing that we don't always need that design level in conditions when we're not at design cooling or when we're even at heating, that we're going to have the duct overpressurized unnecessarily and our dampers would really stay mostly closed in response. So if we open up those dampers, maintain the CFM we need through them, we can have this duct static pressure reset, have some fan savings associated with it. So there's a few ways we can do this. I'm going to go over the 3-part Unified Facility Criteria guidance on how to do this. So the way that it's spelled out in the UFC is you start on the left here by taking in VAV damper commands. So all of your zones would report back to something like a plant controller what their VAV damper position is. Is it 20%, 50%, 100%? The maximum and the minimum of all those commands are noted here and then sent to these comparator blocks. What we're trying to do is understand, do we have any zones that are above 90% open or any zones that are below 50% open? If we do, we may want to ramp up or ramp down our set point. So that's basically what we're doing here, is understanding, do we need to change the set point in some way, or is everybody mostly happy between that 50 and 90%? Once we've established if we're going to ramp up or down, we'd go to the second part, which would be using a fixed supplier pressure set point rate. So here it's identified as 0.01 inches of water column per minute. So that's how fast we would change the set point. And when we're enabled, we would create this new supplier pressure set point offset. So fixed rate of change, and that's to add some stability to our loop so we're not all over the place with pressure or risking some type of damage to our ducts possibly from a poor control loop. And then passing that supplier pressure set point offset to this final stage where we're adding that to some pre-configured or default number. So maybe that number is the 1.5 inch design, maybe that number is something in between in the middle of your reset range, but you're modifying from there what that new offset is, adding those two together. With these max and min blocks, you're making sure that you're not above or below some extreme range. So if you know you want to operate somewhere between 1/2 inch and 1.5 inches, those would be your low limit and your high limit. And then establishing that, sending that out to your system as your supplier pressure set point that would be changing. So as I said, different ways to do it, but the way that we show in the UFC, it is still a reset, even though we're not using a PID block. Number of things with the pressure sensor that we pointed out with the supplier pressure loop that would still apply here in the reset application. But some new things we want to consider is this concept of rogue zones. So are there zones that are driving your reset or limiting how often you would be resetting? So the first thing to consider is, which zones do you want as part of this reset? Are you going to pull in every single VAV damper command at the first part of that sequence? Or are you going to ignore the damper command from certain spaces that are not occupied or are tolerant of possibly not hitting their temperature set points at certain times? How aggressive do you want to be with this reset? Also, consider the system that you're applying this reset to. Do you have a large system with a lot of box and possibly a lot of small boxes that may be at 100 or 200 CFM as their set point? If that's the case, you may find that you're not going to hit your reset as often as you may like. There may be a small box acting as that rogue zone because it's very easy to only want a few hundred CFM. And most importantly, who's watching this system? So one of the things that we need to keep in mind with our reset is that these things really need to be watched to make sure that we don't have rogue zones either from some error or some poor application or a box that may be better off being removed. We want to be able to catch those things in the early stages of this reset to make sure that we're getting the most out of it. So on this front, ASHRAE's actually required some pretty ambitious things, including having a front end alarm that gets sent when specific zones are excessively driving the reset, and having some way to readily allow BAS operators to change which zones are part of that reset logic. So that can be easier said than done to get that into a system. It's possible, but this really just, there's a problem in the field with not getting the most out of our reset sequences, and that we need to watch them to make sure that they're working how we intended. So we talked about the supply fan. What about the return fan? How might that be operated. So remember that with the return fan, what we're really trying to do is add enough inches of water column to get past the pressure drop associated with the return ductwork. So a few things to keep in mind. One is if you can avoid having a return fan in your system, that would obviously be ideal. If you had short duct runs, large duct, maybe a plenum return, whenever you can have low pressure drop such that your supply fan can accommodate that extra bit of pressure without overpressurizing your space, but getting the air back to the air handling unit. So small units, that might be a consideration. If you have a return fan, finding out if you actually need it, or if you shut that off, if the fan can pick up that load without overpressurizing your space. Find that we really do need a return fan in something like a VAV application, both because we want to avoid overpressurization for certain code issues, and because we can have a better operation when done right with our overall system. So there's a couple different ways that we can control the return fan. The first is with speed matching. Now this isn't recommended, but one of the things you could do is take the command, the 0 to 100% speed command going to a supply fan VFD, and send that same control signal to a return fan VFD. So as we saw with pump and fan curves, there's some very specific operating ranges between pressure and flow that these systems operate at. So there's no guarantee that we're really going to meet our design intent by just using speed command. So we want to avoid that. We could go off pressurization in our space, so having a space sensor that is telling us when we're overpressurized to speed up the return fan. But that's really better suited for single zone applications and more of how we might run something like a relief fan. And finally, we could do flow matching, and this is really what we recommend, is having airflow stations in the main supply and return ductwork, having some offset between the CFM supply of your fan and your return. So understanding that you want to have some slight pressurization in your space and accounting for some exfiltration, you'd have your return fan slightly offset, and we might call that DDC point the flow differential or difference set point. So having that difference, then controlling a separate return fan loop to send out your speed command just to that return fan. So schematically, this is what that might look like. We're taking in both airflow readings from the supply and the return, applying that delta, running that through something like a PID loop, and then sending that command as a return fan speed. So we see the supply fan tracking on the bottom, very basic, and the preferred return fan control with airflow matching on the top, where we're taking those two inputs from the flow stations on return and supply flow, taking the delta, comparing that to our set point for what that difference should be, and then having the PID with its different settings and with a fan enable, sending out the new control command to the. So we've looked a lot at individual control loops that are really at the heart of the HVAC control sequences. But we also want to recognize, and I'll make this example with the return fan logic, that there's a lot that goes into it on the outskirts of those control loops. So here we have a system enable that's doing a few things. So there's no PID block here, but the system enable that we saw that drives those PID loops will originate from something like this, some string that is looking at these types of considerations. So we can see a few things. Just looking at the extremes, we notice that there's inputs for fan status, some temperature, some occupancy status. On the right, we're seeing that there's some failure alarms, some enables, some start-stops of our fans. So if you start at the left here, and we start at the bottom left, we can see that these temperatures are being compared. So we're looking at the lower limit set point of a space. How cold are we going to let a space get when we're unoccupied? Comparing that to an actual temperature, this hardware input, and then finding out if that delta is enough to start a fan request or if we're in occupied mode. So either of those will get passed forward, and assuming that our fan isn't disabled for some reason, we would send a fan enable signal as well as a fan start-stop hardware signal. And assuming that we're in occupied mode, that would also go to a system enable where we might start other systems such as a chill water or hot water system. So we also see that fan enable signal being passed this on delay timer block. So what we're doing here is after 30 seconds of saying the fan should be enabled, we're taking a look and seeing if we're actually getting fan status at our return and supply fans. So with some CT or current transducer, checking to see if those fan systems are actually energized. And where that's not the case, we're going to send this fan failure alarm. And that can be a whole separate set of control blocks that we might see. So looking at that fan failure as well as some other hardware inputs for smoke or mixed air low limit or supply air high limit, we might send alarms as well as turn our system off and have it be reset with this hardware button that would reset this latch and then allow that fan disable to go back to a 0, or essentially allow the system to be turned back on. So these would be alarms that you would want a maintenance person to come and physically reset some button, acknowledge why they had the alarm, to turn things back on. And we could have a number of informational alarms, like understanding that we have high pressure drop and we've tripped some filter switch and sending out some alarm to an energy manager or a maintenance personnel to be able to do some spot replacement. So, some thoughts. We want to be aware of what design assumptions are built into our system, both with the pressure set points that we're using, with what the intent is of something like a return fan, as well as how our system is enabled and when it should be operating. We want to be aware of the configurations that we have. So do we have a return or a relief fan, and are they be running as such? And we want to pay attention to what might happen if things aren't enabled or disabled correctly. What might come on at nights because of the combinations of if, or, and then statements. What might happen if one fan comes on but not the other. So be aware of all the implications of this logic and maybe consider what type of things you could test to find out what the system's actually doing if the logic becomes difficult to interpret. So we talked a lot about airside systems. Let's look at some hydronic systems and the logic that we might put into place there. So what might we call this system? We looked at it in the piping system videos. If you remember, we called it a primary-secondary hydronic system. So it's a chill water system where we have this common or bypass or decoupler at the plant that allows these loops to more or less operate independent of one another, hydraulically speaking. So what do we do here? What's different? So we still have this primary-secondary configuration, but we've added a VFD to the pump on the secondary side, and we would call this a primary variable secondary pumping loop. So let's look at how you might set up the logic for that. So here we see again we're using a PID block, and we're using some pressure down in the system, comparing it to a set point to send out some VFD pump command. And the enable there can be done a number of different ways. And here we see we're looking at cooling requests for this chill water system. So presumably, is my temperature deviation such that, or do I have a valve command at a certain percentage such that I have a cooling request? And should any one of those start my system, start my pumps, and enable this PID loop? So there's different ways it can be done. Typically for a heating system, you might require a certain number of heating requests to be able to enable things. But the way they have this cooling request set up is any one of them can enable the systems, the pumps, and the PID loop. And like we've seen in a couple different times, we're seeing this pattern where we have a set point that we may want to consider resetting to match some actual load condition. So some thoughts there. So as we turn down pumps and motors, especially where we have resets in place, we want to be aware of a few things. So the pumps and the motors themselves are going to require some minimum speed to cool off. And there's some rules of thumbs out there. One that we've heard is about half a GPM per horsepower is going to be enough on the pump side. But there may be some manufacturer recommendations or specifications to how low you can turn down the motor and what the minimum flow is on pieces of HVAC equipment like a chiller or a boiler. So be aware of those. And just like with our airside systems, we want to be aware of where the pressure sensor is and how it's located in our pumping system. So there's a couple different ways to do that, but the best practice that we see is with the differential pressure sensor that is really as far down the system as we can, that is looking at the difference between the supply and return. And as valves close, the pressure sensor will increase the PSIG that it sees, and as part of that control loop, drive the pump down to accommodate that lower load situation. So even better would be if you had somebody that, as part of a tab or recommissioning event, to look at the actual differential pressure associated with design flow and to modify that set point accordingly, or resetting that set point so that when all those valves are closed, and if you have that communication between zones and plant, and you see that just like with our duct static pressure set point reset, where we had dampers closed, where we have valves closed, that might be an opportunity to reset that hydronic supply pressure set point. So that's going to wrap up our discussion on HVAC sequences of operation. There's quite a bit more we could say here, but we just wanted to lay the foundation for how we can think in terms of control logic blocks to be able to aid us when we go out into the field and we're reading these drawings and trying to think about how we can manipulate sequences to repair some problem or to improve or optimize the performance of our systems. And now we're going to move on to some other drawings like point schedules and some different schematics that we also want to be able to understand when thinking about the performance of our systems.